Okay, so to continue our discussion of hybridized orbitals, and it's now Sunday afternoon, a little bit of a time gap. And so we're going to look at three different structures, and this would be a classic example of sp3 versus sp2 versus sp hybridization. So we're going to start with ethane, C2H6. So here I've got the molecular structure for ethane. And remember on your organic stuff, anes mean single bonds, enes mean double bonds, ines mean triple bonds, okay? So this is simple. You got ethane C2H6. So if you look around the central carbon atom, you have 1, 2, 3, 4 regions of high electron density, and that's counting this bond between this carbon. So you have 1, 2, 3, 4 regions of high electron density. So this is going to be sp3 hybridization. So if you look at that bond angle, it's 109.5 degrees. You have an even distribution. You've messed up the s orbital, and this is going to be important. You've also messed up all three of the p orbitals, okay? So you've messed up the s, and you've messed up all three of the p. So listen to me. There are no non-hybridized p orbitals available. Everything is jacked up in that second energy level, okay? So here we've got ethane. 4 regions of high electron density, sp3 hybridization. Now, in contrast to that, now we're going to look at ethene, which is C2H4, okay? Now, with ethene, here's what you want to look at. So, this is going to involve a double bond, okay? This is what this is going on here. So, to have C2H4, you've got your carbon, okay? The double bond here, the hydrogen, the hydrogen, hydrogen, hydrogen. Now, when you have a double bond, there's sigma bonds and there's pi bonds. Sigma bonds always involve single electrons. So if you look on the number of bonds, like for example, with ethane, those are all sigma bonds. When you have ethene, when you have a sigma bond, and then you're going to have a pi bond. Ethyne, which you're going to see has 3 bonds between the carbon, that's going to have a sigma bond and 2 pi bonds. So the maximum number of sigma bonds you can have is 1. Anything above that has to be a pi bond. Well, you'll see also this is going to be like a logic problem on how this deal plays out. So let's talk about what type of hybridization we're going to have. So if I count around this central carbon atom, there's 1, 2, 3 regions of high electron density, okay? So that means that it can't be sp3 hybridization, it has to be sp2 hybridization. So this is going to be sp2. Now here's what's most important. When you look at this central carbon atom on this one, here's this carbon atom. So we're going to have 3 regions of hybridized orbitals, okay? Now, but here's what's important. Remember, your p sublevel has 3 orbitals. What we've done is that we've messed up one of the s, and we've messed up 2 of the p orbitals. Here's what that's important. What that leaves us is a non-hybridized p orbital. That's what you have to form a pi bond. So, and this is what's tough to draw, but imagine if you will, let me get rid of this. Imagine if you will that I've got a non-hybridized p orbital that's coming out like this. That's in the plane of this page. So, I'm here, okay? So I've got this carbon, here's one of these, here's the second hybridized orbital, here's the third hybridized orbital, and now sticking out from there, I've got a non-hybridized p orbital. Now, the same thing is going to happen over here with this carbon. Okay, so it's going to overlap, there's going to bond, there's a bond, there's a bond. Okay? So this is also going to have a non-hybridized p orbital. So this bond is existing out here in this plane. So, because remember, your p orbitals exist on the x, y, and z axis. So what's happening is that I've got a sigma bond in between. I've got a sigma bond here, sigma bond here, sigma bond. Now, hydrogen, if you think through it, hydrogen can only form sigma bonds. Hydrogen doesn't have a pi bond available, doesn't have a p orbital to form a pi bond because it doesn't have a p orbital. Carbon can because of the fact that it has a non-hybridized p orbital. So, I'm like this. I've got the sp2, so I've got 3 regions of high electron density. The s, 2 of the p's, that leaves me a non-hybridized p orbital. I've got a double bond, and then I've got the carbons around here. Okay, now let's talk the last one, which is going to be ethyne. Okay, so let me kind of get rid of this. And no, I haven't found my dongle that is going to allow me to connect my board or my iPad to my projection system. And yes, I'm not happy about it. Okay, so this is going to be C2H2. So what we're going to look at here is this is ethyne. So notice on here I've got 1, 2, 3 bonds, count them, 3 bonds, that exist between the carbon atoms, and then I've got one region out here with this hydrogen. So if I count around this central atom, so I've got a carbon, triple bond, carbon, hydrogen. Okay? So this is very much a linear molecule. So what happens is that one of these is a sigma bond, and then I've got to have 2 pi bonds. Now, if you remember what we just talked about, you have to have a non-hybridized p orbital to form a pi bond. So this is where this hopefully now all makes sense. So now you could look at this and go, oh, okay. So I've got 2 regions of high electron density. So that means that's going to be sp hybridization. So I went from sp3, where I had 4 regions. I had sp2, where I had 3 regions. And now I have sp, where I have 2 regions. So remember, when you're adding them up, there's always a 1 that goes with the s. So this is why this is in effect 2 regions of high electron density. So here's the common mistake. Everybody goes, oh, well there's 2 regions of high electron density, that should be sp2 hybridization. No, 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 no. There's always a 1 that's associated with this s. So you add these together, that in effect becomes 2. So this is sp hybridization because I have 2 regions of high electron density. This has 3 regions of high electron density, that's sp2. That has, the ethane has 4 regions of high electron density, that's why that's sp3. Now, so this is going to take a little bit of drawing on my part, okay? So stay with me here. So on those central carbon atoms, so stay with me through my artistic struggle here. So I've got a carbon atom, and here's this sp, okay? So I got hydrogen out here, So this is my sigma bond right there. That's a sigma, trust me. So now what happens is that now on this axis here, imagine that I'm in the plane of the board. So I'm going to have a p orbital, a non-hybridized p orbital here, and that together is going to form one of my pi bonds. Okay? So this together, this whole thing here, that's in the plane of the board is making one of the pi bonds. Now, coming out of the plane of the board, like this, okay? So imagine this is coming out here like this, okay? All right? So coming out here like this, now I've got a second non-hybridized p orbital, okay? So Excuse me. So there's the second pi bond. So I've got a sigma bond in between. Then I've got a pi bond in the plane of the board. And then I've got a second pi bond existing out here in the axis coming out like this and then into the board. So this is where this is, it's a logic thing. Oh, I got a triple bond. I can only have one sigma bond. To form the other pi bond, I've got to have a non-hybridized p orbital. So this is going to require two non-hybridized p orbitals to form that double bond. So ethane, all single bonds, sp3 hybridization, all the orbitals are jacked up. sp2, you leave one non-hybridized p orbital. Ethyne, where you have sp hybridization, you have two non-hybridized p orbitals. So that's what you've got to think through. Now here's something important also that happens. These models actually show a nice job of showing this. So if you look at ethane, okay, kind of looks like a dog. And if you look at ethene, and then if you look at ethyne, now here's something that's important that happens. Hopefully you can see this. Notice what happens is that the carbon atoms actually become closer together, and the models actually do a nice job of showing that. So what that means is that the more bonds that you have between these carbon atoms, the closer those nuclei are going to be. Because of the fact that you have these bonds that are holding these atoms together. That oddly enough means also that it takes more energy to break those bonds because of the fact that you've got to break a single bond, that sigma bond, and the two pi bonds. So this is the classic example of what's going to happen with these bonding structures. sp3, 4 regions. sp2, 3 regions, sp2. So go through the notes. You've got to kind of let this soak for a while, but at the end of the day, it should all make sense. So the rest of the stuff I'll do with my iPad, but I wanted you to be able to see these models. So that's the story, kids.